Thanks. So I'm from Berkeley Laboratory, and this is the view of Berkeley and San Francisco from our lab. Berkeley Lab was actually the first Department of Energy National Laboratory. If you've seen the movie Oppenheimer, you can see here some of the players. There's Oppenheimer there. We have E.O. Lawrence, who did the first atom smasher, Teller, and they're all sitting here on top of the magnet here of the first very large atom smasher that split the atom. And so that's in 1939. This is when they were still scientists and before Oppenheimer went to do the Oppenheimer movie. But the lab today has grown from this to one point. This is actually old information. We're about a $2 billion this year, and it says 13 associated Nobel Prizes. We're now at 15 a few years later. So I work, though, in the computer science area, and my department it works on designing both the hardware and the software for the next generation of supercomputers. And some of the key things that we use supercomputers to do are, creating. They take snapshots with the telescopes all around the world of every star that can be seen in the night sky, and we process that data every night to search for supernova or other interesting celestial events that they can point, so they can see them one night in Australia, and then when the world turns around, they're ready to then focus in on events that are really interesting when it turns around to the US side of the globe. Predictive biology, we do brain scans like our previous speaker to understand speech production, designer materials, and also processing all of the data from the particle accelerators that are now primarily located in Europe, in Switzerland. So, in order to get to the next generation of the next level of performance, we've been working on, for the past 10 years, on this Exascale Computing Project, which just wrapped up this past year. This had equal investments in application development, the software technology, and hardware technology, in addition to the investments in the systems themselves. And this was a goal to go from petascale, which is 10 to the 15th power operations per second, to exascale, 10 to the 18th power. And this was a huge undertaking, about a $3 billion project, and recently delivered at Oak Ridge the first system to achieve that goal. 10 years ago, or well, more than 10 years ago, in 2009, we projected that energy efficiency and power consumption was going to be the leading factor that keeps us from achieving that goal. And in fact, we set a goal for ourselves in this project to do an exaflop with 20 megawatts of peak power. And indeed, we came in just under that goal, one exaflop with 21 megawatts of power, just over that goal. And so it became the #1 in the top 500 list of the largest supercomputers in the world, but it's no mistake that it was also #1 in the Green 500, which is the most energy efficient, because that was crucial to achieving that target. And the estimated cost, though, for this machine, we had 2 machines, and each one cost about $800 million. So now this is the top 500 list. This has been used for the past 3 decades to track our progress in terms of improving the performance of supercomputing systems. This uses the LINPACK benchmark, which is a dense matrix benchmark. Some today we consider it a little bit too easy because it's too oriented towards floating point operations. But if you look at the progression here, so this is these 3 lines here. This is the #1 system on the list of the top 500 most powerful. The orange line is number 500 on that list. And then we have this blue line, which is the sum of everything in the list. And historically, we've seen about 1,000x improvement every 10 years. But if you fast forward to today, things are starting to slow down. This is log linear plots are hard to really see what's really going on, but this is doing a linear plot of the same thing, and you can see here that we had this era where it was consistently 1,000x improvement in performance every decade, and we've been going downer, 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 and right now we're down at 3x every 10 years, which is a huge reduction in performance. And what this means is that HPC's future is going to look like this if we continue with business as usual. The second is, if anybody tells you that Moore's law isn't in trouble, hasn't been looking at diagrams like this. Moore's law, they're able to shrink transistors, but they're not as effective as they used to be a decade ago. And for our next generation of system, we've gone from terascale to petascale to exascale, but scale alone really isn't delivering more for our community, and it's not solving this problem. People say, well, why don't we just stick with exascale? Why do we need a more powerful supercomputing system? And this here is kind of an example. So kilometer scale climate modeling. Right now, the state-of-the-art climate models are 25 kilometer or so, and they don't resolve all the details of the mountains. And this is the biggest source of errors in existing climate models. Not only do they not resolve mountains, they don't resolve individual clouds. They see a whole patch of area, and they treat all of the clouds in that giant patch of area as a statistical probability distribution, and that is also known to be a source of error. We really want to be here at this 1.25 kilometer. This is called a cloud resolving model, which can resolve mountain peaks, but also resolve individual clouds and treat them as physical processes rather than statistical approximations. So recently on the Exascale supercomputing system, Frontier, they achieved 1.5 simulated years per day performance for a kilometer scale model, and not even necessarily at our target, but at that rate, to do an ensemble calculation of over 400 years, it would take 20 years of dedicated computing time on the most powerful supercomputer in the world to get an answer that we need for our policy goals. And that means, to achieve our target in 2055, we won't get the answer until 2045. So that's unacceptable solution. And this other diagram in the bottom here says, well, why don't we just wait for a supercomputing system to come around that'll be able to run at the performance that we need? And the answer is we'd have to wait until 2055 for that to naturally occur, given the current rate of progress. So that's not an acceptable outcome for a future where important scientific imperatives that have global consequences that we need answers to. So we can't stop where we're at. We have to move on. So here's the underlying problem. The underlying problem is there's an explosion of computing demand across the industry, driving this need for a hyper-exponential improvement in energy efficiency and integration. What we're seeing with the AI explosion here is we've gone from a Moore's law tracking demand to one that's hyper-exponential, where demand doubles every 3 months instead of every 2 years. And yet the supply for computing is not growing at historical rates. In 2005, Dennard scaling ended, and so our ability to improve the energy efficiency of machines is not improving at historical rates. You combine this together, and it's creating an energy crisis. For example, this is Google's sustainability page last year in 2023. In fact, if you can look for Google sustainability, and you'll still see this picture. I don't know why they show that picture, because 1 year later, Google's AI ambitions threaten carbon neutrality pledge. Since 2019, they've actually increased their power usage by 48% rather than decreased it in moving towards carbon neutrality. So they're failing in their promises. We suspect that the other hyperscalers are too, but they won't share data. And the net result, though, here is that the energy consumption just from AI alone is on track at the current rate of growth to dominate worldwide energy production. So imagine right now it's like 4% of worldwide energy production. Within a decade, it's going to be the dominant factor for the future of worldwide energy consumption, even beating manufacturing and arc production of metal. And it's probably going to be limited first by market dynamics before it actually eclipses worldwide energy consumption. But the market dynamics right now say that for every dollar of investment in a new GPU to power one of these data centers, they get $5 return. And so they keep on buying these things. NVIDIA now charges $30,000 per GPU, and you still have to wait 52 weeks for them. And so with those kind of market dynamics, and they consume, the last generation consumed 300 watts, the current one 600 watts, the next generation 2,000 watts per GPU. And there's no governor to slow that wheel down. The economics are pushing us towards this energy limit here. This is another picture from from AMD a couple of months ago. I snapped a picture. So the training of ChatGPT in a Meta AI cluster is equal to the total power consumption of the countries of Ireland and Germany combined. And that's today, so it's going to get worse. It's unsustainable. So what do we do about it? Computer architects, the go-to in order to create a more energy efficient system is specialization. It's not just a computer architect's tool to create a more energy efficient system. It's also nature's way of extracting more performance when you have a resource limited environment. So, just looking at the progression here, you got your powerful general purpose computer processors like the IBM Power and the Intel Xeon processor, represented by this Raptor here. In 2005, we lost Dennard scaling. Dennard scaling was our ability to reduce the voltage each generation in order to improve the energy efficiency. And that's led to our current, energy crisis. So when you have food scarcity, like post-Dennard scarcity, you end up with a lot of smaller creatures, like this half dozen really aggressive sparrows. That's really what happened when we went through the many-core era, which was Intel Knights Landing, AMD, the Cavium Marvell systems, and to a certain extent GPUs. Lots of lighter weight animals, lots of lighter weight processing cores, all working in tandem in order to produce a result. But once you go to post-Moore's law scarcity, the critters got to go after different food sources. You end up with them evolving specialized beaks in order to go after those food sources. And that's where we are today, where Apple, Google, Amazon, and Microsoft are pursuing a strategy of specialization to target different parts of their workload. But they're learning ways to introduce that specialization in ways that are economically feasible. Even though they have an amazing amount of money, you can't be wasting it. And so that's what leads to chiplets. So right now, the state of the art, if you look at these GPUs, they're 800 square millimeter reticle limited designs, these massive, massive processors. It's very, very expensive to produce, and both in terms of engineering and manufacturing costs. So chiplets is an alternative way to construct these kinds of mega chips, but offer ways of tailoring a chip for different markets at a much lower cost than a reticle limited design. The way they work, and I'm just using a planar example here, is that normally you have these pins here, and they're kind of big, and they haven't historically improved according to Moore's law. So Moore's law says you can double the number of transistors you can cram on a chip every 2 years. There's no such Moore's law for pins. The number of pins has stayed relatively, it's increased, but it's only 1.5% compounded rate of growth versus the 34% that you have for Moore's law. So the result is that you have to increase the data rates for these pins, and it gets harder and harder, and it just hasn't kept up with the growth rate of compute within the chip. So instead, you can use obsolete lithography technology to engineer these little solder microbumps or copper micropillars onto the bottom of the chip. And now you can achieve a Moore's law growth rate for the number of pins. Now you don't have to operate those pins as fast. You can run in a regime that is more energy efficient, and you can have massive bandwidth between these chiplets, and you can beat up on those big monolithic chips using a bunch of these smaller ones, each one specialized for a different piece of functionality. And this is how we can achieve, so this is advanced packaging. This is how we can achieve energy efficiency, but also modularity. Now I want to make clear that I'm talking about 2.5D here because it's easier to talk about in PowerPoint, but there are a lot of different approaches to this advanced packaging to co-integrate these chiplets in 3D and as MCMs and other ways, but we're going to just talk about 2.5D just because it's convenient. Now, chiplets, the key thing is I was discussing, they lower manufacturing and design costs. The very first thing that they do is that right now these mega chips from NVIDIA and others, the monolithic chips, they achieve, when a new process comes online, a 4% yield rate. That means for every 100 chips that come off of the assembly line, 90% of them you're throwing in the trash because there's the probability of a defect that's fatal goes way up. A chiplet would be about 100 square millimeters, so you're over here in the yield curve, and the yield curve improves dramatically where you'll get 50% of your parts will actually work when they come off the assembly line, or even more, 75%, whereas you're still at 20% if you stick with the reticle limited design. The second is that not everything that you need on a chip needs to be at the leading edge design node. The leading edge node, like 2 nanometer today, is obscenely expensive, the mass cost for setting up production. And yet things like memory controllers and SerDes and PCIe don't benefit from being at a leading edge node. That's good for increasing the density of the compute parts, but for a memory controller, it doesn't matter. So you could go to an older technology that's much less expensive for your memory controllers, and you can partition your functionality and assemble into a single system and package that has a mix of leading edge for the stuff that really needs it, but the majority of the package can contain stuff that's an older, more cost-effective node. And it also allows for reuse. If I have a high bandwidth memory controller, there's so many different projects I could reuse that against. Why should I have to respin a chip, an entire reticle limited chip, which is crazy expensive to get access to that kind of IP? So I can have also startup companies could have access to a very effective high performance memory subsystem without having to own all the IP for that. So the last part, though, and this is the important part for HPC and the future of HPC, but also for hyperscalers, is domain specialization. So as I was mentioning, you get to reuse IP for things that everybody needs, the Linux bootable cores, your SerDes, your memory controllers, but you can drop into it special functions that are of interest to you that you would never be able to convince Intel or AMD or NVIDIA to include into their chips, like an FFT or a QR decomposition accelerator that is important for your workload. And it integrates with tens of terabytes per second of performance, so not limited by the PCIe where you have these long wires. By co-integrating these things in the package, you get massive data movement, energy efficient data movement between these accelerators. And that's the part that's really exciting about moving to this kind of advanced packaging in order to get domain specialization, but also get access to this leading edge, commercially supported IP, because the cost of the platform, the compilers, the firmware, all of the other things, even the people who make the cooling systems for these things, chiplets allow you to get into the platform and reuse all of the platform's IP as well, rather than having to own the entire chip. And we know that HPC can't afford to own the entire chip anymore. And neither can the hyperscalers. So this is really a general movement in the entire electronics industry to move from a transistor focus to a system focus. 5 minutes, okay. So, you know, our old economy was based on shrinking the transistor, everything got better. Now we're moving towards you have to design systems that are tailored for the problem that you're trying to solve. And this is from Meta, where they basically see that their workload, there isn't one kind of AI, there's lots of different kinds of AI, there's lots of different workloads, and that they're seeing this splitting of their systems to create specialized systems that focus on those different areas. Neil Thompson spoke last year, and this is one of the slides that he presented as well. He's a colleague from MIT, about the need to co-design software, algorithms, and hardware together in order to maintain that systems focus. So, industry is not caught flat-footed on this, but I think there's a lot of learning we need to do in the HPC community to take advantage of what the rest of the industry is doing. Attack of the Killer Micros in the 1990s was about following the trends of the rest of the industry and leveraging those trends to serve HPC. AMD has published its chiplet strategy, showing that it is more cost-effective to do instead of a reticle limited design, do it in chiplets. But another thing that's interesting that they offer is, well, what happens if we wanted to insert a specialized chiplet for HPC into their platform? And that leads to the last part of the presentation, which we'll finish in 5 minutes, which is, what are the kinds of things? This is the future of research for HPC, is finding out what kinds of architectural specializations would be particularly effective for science that we could insert into these chiplets platforms. And that's the interesting thing. So very quickly, one example is density functional theory. This is a material science calculation. Material science calculations allow us from first principles, by calculating directly from first principles the electron cloud of a material, we can predict its performance, the tensile strength or the electronic properties, in this case, of a transistor, before you've ever even synthesized the material or designed the device. And it is quarter to 1/3 of all HPC cycles in the entire world, so it's a big ticket item. And it happens to have a very dense algorithm in the middle that hasn't changed very much over the past 30 years, that's got order n cubed complexity, dense matrix multiply with 3D FFTs. These are things that we know that we can hyper accelerate using specialized circuit designs. And so we're thinking of creating a specialized chiplet to target the core algorithm of this material science code that's pervasive across the entire world. Now you have to reformulate things from the traditional von Neumann, which is instruction processing. I do this, followed by this, followed by this. Processing instructions, and you invoke these kernels sequentially. Instead, when you do a circuit design, it's data flow. And so you have to flow your data through. All the computation is stamped out and it's static with data flow paths between it. And so it's a really interesting way to rethink all of the underlying mathematics for your algorithm in order to be able to create specialized accelerators in this fashion. And so we're creating these language called Chisel, which enables us to rapidly prototype fully parameterized design generators. So instead of writing your hardware design, you write a generator that you input the parameters that show the pipeline depth, but also the width of your design, and it'll generate that hardware for you. And in doing so, you can create something that takes only 0.1 millimeters of area. So remember, those are 800 square millimeter chips. Just with 0.1 millimeters of area, I can outperform an entire GPU. Okay, so there's a big opportunity here to increase the efficiency and the effectiveness of these things. We also have things like data rearrangement engine from Lawrence Berkeley National Lab, which is able to take stuff next to the memory controller and rearrange it so it can be processed effectively and efficiently by the processing cores. We also have co-packaged optics. There's a confluence with that advanced packaging technology, but also these silicon photonics, which have these little ring resonators that encode light on different frequencies of light. So individually, if you wanted to do 100 gigahertz, through one of these optical pathways, it would be impossible. Here, I have 100 wavelengths of light, and I get an aggregate of 8 terabytes per second data link. So not 100 gigabits, but 8 terabytes per second. And I can use these comb laser sources also to generate all those frequencies of light simultaneously. So we can have massive bandwidth between chips using photonics. Because in electronics, resistance limits the distance you can go. But with photonics, once you get in that domain, you can go anywhere in the system at multiple terabytes per second. And it also allows you to reconfigure your systems to target different parts of your workload as well. All right, so we've built a platform here that allows, is open source, so researchers can experiment with chiplets and co-integration of diverse accelerators in the platform. It uses RISC-V, but we normalize the communication, so everything, instead of having to have a software driver for everything, they all speak a common language once you drop them into our sandbox. So you can check out this development platform and prototype using FPGAs to experiment instead of having to tape out. AMD has publicly announced that it is offering what I described earlier, a spot in their platform for third parties to plug in their stuff, and we're creating Mosaic is 100% compatible with AMD's Infinity Fabric, so you can prototype using open source and then hand over the idea to AMD so it can be inserted into their commercial platform. And that's the road we're moving towards here, is open chiplet marketplace. Right now, we have these vertically integrated proprietary platforms. AMD is now offering this semi-custom, third parties can drop into the AMD platform. Intel will be offering the same very soon. But we're moving towards this vision for an open chiplet marketplace where you can see that ARM now offers all of its IP as chiplets now, and you can co-integrate ARM chiplets with multiple parties. And that's kind of the future we're going to go to. So, last slide. So the opportunity for HPC is to leverage the larger market to create a new economic model to get targeted specializations, because we are built on this pyramid model where there's a big market supporting us below, and we need to concentrate our resources on the part that makes a difference for science. Because if we don't, we're not going to be big enough to attack the city anymore. HPC is not able to do this on its own. It has to follow the industry. That's it. Thanks.
Perfect. A big round of applause.